Welcome to Hot Chips 34. Session 7, Mobile and Edge Processors.
Welcome back for this very last session of this conference. I hope all of you are wide awake after this long day because we have, 4 really stimulating talks, and we are all going to be, getting a lot of interesting facts on the latest and greatest for the different CPUs in this session. This is Devjit Das Sharma, and it's my honor and pleasure to chair this session. The 4 talks that we are going to hear are from AMD, Intel, MediaTek, and another one from Intel on their latest client CPUs, as well as smartphone SoCs and edge processors. Please, write your questions on the Slack, and I'll be picking up questions from there and asking at the end of the talk. And without further ado, let me introduce the first speaker, Jim Gibney from AMD. He's a fellow SoC architect working on the next generation client processors. He received a Bachelor's of Computer Engineering and Master's in Electrical Engineering from Georgia Tech in 1996. He worked at Digital Compaq on Alpha server chipsets until 2003, when he joined ATI to work on gaming console graphics processors. His interest area is memory system architecture for high-performance notebook processors. Jim, take it away.
Hello, everyone. I'm Jim Gibney, the SoC architect for the Ryzen 6000 series processor. I'm looking forward to taking you through an overview of the technologies and features in AMD's newest mobile processor. Let's start the presentation with the 4 overall pillars for building a great notebook processor. First, we start with new Zen 3 Plus CPU cores, with many focused design improvements and features to deliver the best perf per watt x86 processor. The second pillar is RDNA 2 graphics, for the first time in a notebook processor. This new generation architecture provides a significant leap forward in graphics capabilities. The third pillar is process technology, specifically TSMC 6nm process technology. The primary focus of the technology node is improved density, which lets us add more capabilities into the product. And the final pillar consists of platform technologies. As we will discuss, there are significant upgrades in our platform interfaces, including DDR5 and LPDDR5 for power-efficient memory access, PCIe Gen 4, USB 4 for peripherals and docking, and the newest platform wireless connectivity. Before we go further, I'd like to show the key proof point for the technologies in Ryzen 6000. We have demonstrated up to 29 hours of battery life with a workload of 1080p local video playback. Delivering outstanding battery life was really the culmination of a huge effort, including architecture and technology development, encompassing hardware, firmware, and software teams. Now I will walk you through an overall block diagram showing the internals of the Ryzen 6000 series APU. It is a complete system on chip with CPU, graphics and other accelerators, memory, and I/O subsystems. On the top left corner are the Zen 3 Plus CPU cores. Zen 3 Plus supports SMT and hence a total of 8 cores, 16 threads with 16 megabyte L3 cache. Moving counterclockwise, we show the memory subsystem, organized as 4 32-bit logical channels. Motherboards may be either LPDDR5, based for power efficiency and high bandwidth, or DDR5 for systems that prefer SODIMMs and DDR advantages. The interface scales to higher bandwidth levels, up to 100 gigabytes per second peak, which is especially important for feeding the graphics subsystem. Speaking of graphics, as we continue counterclockwise, we show the RDNA 2 graphics engine. Up to 12 new RDNA 2 compute units are shown. These are organized as 6 workgroup processors sharing a common 2 megabyte L2 cache. The upgraded memory bandwidth plus the increased L2 cache meant that we hit our uplift targets without needing to add a Navi 2 Infinity cache. Advancing to the right, this takes us to the new Microsoft Pluton processor, which adds enhanced security features and which integrates alongside the AMD platform security processor and enables secure boot and provides hardware root of trust. There's a new display controller supporting 4 independent displays with updated DisplayPort and HDMI protocols, supporting high-resolution displays at high refresh rates for smooth graphics. Next, we show our internal system management units, essentially the control center for SoC power management and power delivery control, and the integrated Fusion Controller Hub, which includes platform support and control IOs. Continuing, we have multimedia engines, including video acceleration for both decode and encode acceleration of a number of modern coding formats, and our audio coprocessor, which we will highlight later in the presentation. As we get to the right side of the diagram, we have an integrated sensor fusion hub for managing sensor inputs in a modern notebook. And finally, moving to the upper right, we show the new I/O subsystem and platform connectivity, including PCIe Gen 4 for fast storage and other peripherals. Our USB subsystem includes multiple Type-C ports with display alt mode for display support. And now we have USB 4 ports with 40 gigabits per second of bandwidth for docking and storage and peripherals. Ryzen 6000 adds a wireless manageability subsystem to allow administrators to connect securely over wireless to perform IT functions. Finally, we have our Infinity Fabric subset as the main data network on chip, used for interconnecting the engines with memory. We support high bandwidth at low voltage, which is key to power efficient operation. Now that we've seen the composition of the SoC, let's go into our approach for power optimization on Ryzen 6000. We think of power optimization in layers, starting at fundamental silicon technology and going all the way up to software and algorithms as we pursue our goal to build an energy-efficient notebook processor. So let's introduce the layers. First, we have CPU core architecture as a key element of optimization. We will dive in deeper in subsequent slides. Second, we have graphics architecture. Graphics, performance, and power efficiency is key to a modern notebook for gaming as well as other workloads. And we built our best notebook graphics engine yet in this SoC. Third, we have the overall SoC architecture, which includes the overall chip partitioning and power and voltage domains and other features which span the chip. The fourth layer is platform optimization, which will include industry standard protocols, AMD specific technologies, and capabilities enabled by our notebook system partners. The fifth and final layer is system software, which brings together the hardware technologies into a notebook solution targeted to a particular user's needs. So let's get started with more specifics on our optimization approach. We start with core architecture and the specific features in the Zen 3 Plus CPU core complex, which aid in improved energy efficiency. As the slide mentions, there are over 50 new or enhanced features. What I'm going to do is provide a sampling of the focus areas for optimization. First, we have PC6 or CPU off, which is our all cores powered off state. PC6 restore is the hardware-assisted flow for resuming from this state. The state restore path is carefully optimized to minimize restore latency versus the previous implementation. Next, we have selective SCF CTP save. This reduces the number of save restore registers for the PC6 CPU off feature, which reduces energy usage and lowers state transition latency. Next, we show delayed L3 init, otherwise known as L3 bypass. This is another new feature for PC6 Resume. When the core wake-up is likely to be for a short duration before returning back to sleep, this allows us to save dynamic power through bypassing the init of the L3 cache. And then we show cache dirtiness counter. This is a tracker which can provide input to the policy to decide whether it's beneficial or not to go into a power state. We continue on the next slide with additional Zen 3 Plus optimizations. CPPC per thread. This is the collaborative performance and power control feature, which provides an architected method for OS power policy management. In Zen 3 Plus, these capabilities are per thread and allow implementation of features such as preferred cores for maximum performance. Next, we have CCX Light C state. This is the core feature that supports a new Infinity Fabric power state. The use case is for cores lightly loaded and hitting in cache or in CC1 clock-gated state. Basically, this allows a low-power state with DRAM and self-refresh with a very fast wake latency. We will discuss it further in the SoC architecture section. And then we have enhanced CC1 state, which is an improved lower power sleep state for our CC1 clock-gated scenario. In summary, a multitude of changes were made focused on lowering the power dissipation of low-power states, improving the granularity of control, and reducing the latency and energy used to enter and exit these states. We took all these power state improvements and combined them with timing improvements and physical design optimization to improve the frequency power curve. And this leads us to our next proof point, where we show generational uplift both in CPU and graphics workloads and also in battery life. The CPU efficiency improvements noted previously help yield up to 1.17x improvement in CPU compute at the same sustained power level of 15 watts, and up to 1.3x for a 28-watt higher performance system. For graphics uplift, we achieve up to 1.81x in 15 watts and up to 2x in 28 watts versus our previous generation. Now that I've shown a graphics proof point, let's go into the details of the graphics architecture improvements. Here we go into the second pillar of a great notebook processor, and also a key optimization focus, which is our Navi 2 graphics. I'd like to start with the fundamental Navi 2 design attributes, and then show how we build this into the Ryzen 6000 graphics config. To start with the inherent graphics pipeline, on the left of this diagram, we show the RDNA dual compute unit or workgroup processor. I won't go through each element, but the basic principle is to improve IPC using instruction issue of 1 instruction per clock. The RDNA 2 design takes this design and improves the pipeline for higher speed to achieve significantly higher frequency at the same power level. As shown on the bullets on the right, we also get lower execution latency with this approach. So next we show the specific configuration decisions we made. Essentially, we decided to build a larger and wider engine for notebook graphics than we've ever done before, with 50% more compute units, and we doubled the render backend units and the L2 cache sizes to maintain a balanced design. So next, let's go into the how the components assemble into the final graphics configuration. On this slide, we show the entire graphics engine in Ryzen 6000. In the max Radeon config shown on the left, we combine 6 dual compute units with 4 RB Plus depth color blocks and the 2 megabyte shared L2 cache. Basically, when you combine the RDNA 2 design optimizations with this notebook optimized configuration, graphics frequencies now up to 2.5 gigahertz, and the additional memory bandwidth from higher speed LP DDR5 or DDR5 protocols, you get both the higher peak performance, shown as up to 6.8 teraflops for FP16, and an efficient perf per watt implementation. As a further proof point, let's review the bottom line results on our new Radeon Navi 2 graphics architecture. This table compares Ryzen 6000 versus similarly configured previous generation Ryzen 5000 series at 15 watt sustained power level on the left and 28 watt sustained power level on the right. Consistent with our overall architecture goal, we achieved an outsized increase in perf per watt on the most relevant graphics benchmarks such as 3D Mark TimeSpy. Both at the 15 watt sustained power level for ultra-thin efficient notebooks and even more for 28 watt notebooks, which have more power to take advantage of the improved memory bandwidth and higher frequencies. We achieved these results. Now that we've described the Ryzen 6000 CPU and graphics engines, let's continue with the overall SoC architecture, which is the next level of optimization to build an efficient notebook processor. We start with the power rail partitioning. The diagram on the left is a simplified schematic showing our internal power rail partitioning. The dashed lines show CPU cores and the graphics engine built with internal on-die linear regulation. This lets us balance workload power efficiency with lower platform cost and complexity. These domains also support internal power gating. Along with this internal power regulation, we also add a new independent display voltage domain, shown in green, which can stay alive to drive the display for optimizing static screen display. Next, we show the Infinity fabric. The solid line indicates this is a power-gated domain with multiple subpartitions to gate off regions of the data fabric based on the use case. In addition to the granular partitioning, in Ryzen 6000 we add hardware acceleration logic, shown here as SoC-wide save restore acceleration. These are hardware assist sequencers added throughout the SoC for fast transitions between sleep and wake. As shown, we have also improved power and clock gating pervasively across IP block regions now, including some regions which were previously kept alive, such as I/O and PHY regions. In the next slide, we continue with the description of SoC-wide power efficiency optimizations. We start with Infinity Fabric low power states, C states, where both the residency and the power level are key to achieving battery life goals. We mentioned light C state in CPU context, and here we show how this state works within the Infinity Fabric, shown as DFC1. The key is that DFC1 is a fabric clock-gated state with the DRAM and self-refresh, with a much faster wake-up latency than the DFC2 gated state below. This means we can enter the state and get the power state savings in a more active but lightly loaded workload, which is typical of real-world notebook usage. After the C-state architecture, we mentioned low-power methodologies, which allow us to achieve an efficient implementation. The area and density improvements of 6 nanometer allow us to integrate more advanced hardware into the design. We use optimized libraries across the SoC, in particular on the CPU and graphics engines, to drive the significant perf per watt increases we achieved. We mentioned the fast sleep state restore accelerators in the previous slide. These are integrated tightly within our control fabric, and they are pervasive across all the engines where we want to enter a deep hardware power state and to be able to restore quickly using hardware. Finally, we mentioned some platform power control enhancements to the SoC architecture, which we will cover further in the platform and display optimization sections upcoming. And so we move to platform optimization, which is the fourth level of optimization to build a great notebook processor. It was a significant addition to bring in USB 4 support to Ryzen 6000, with wide support for docking and high-speed peripherals. Our platforms can support the latest wireless connectivity, including Wi-Fi 6E with dual-band simultaneous operation, and Bluetooth 5.2 with LE audio. Our SoC supports up to 20 lanes of Gen 4 PCIe Express. As mentioned, our system designs can support LPDDR5 or DDR5. And we also have considerable display technology upgrades, which we'll discuss further, including the latest AMD FreeSync, DisplayPort and HDMI protocol upgrades. And we also highlight here our AI-based real-time active noise suppression, which we will discuss shortly. In this slide, we go one step further into display system optimizations. The display system is, of course, a central point for visual experience and also a major consumer of power in a notebook, so it deserves a large focus in notebook processor optimization. Some of the display optimizations we enabled in Ryzen 6000 included a new panel self-refresh state, coupled with the power domain partitioning previously shown for very efficient self-refresh operation. We have more granular voltage control at the platform level to drive that new display controller logic, independent of the other SoC rails. We have new additional low power panel support. We support display stream compression and forward error correction technology for DP lane reduction in the platform. We also have FreeSync panel self-refresh with selective update, which saves power by reducing the updates to just the portion of the screen which is changing. And I would like to highlight a key SoC optimization: deeper display buffers, which allow us to maintain deep SoC power states for significantly longer idle durations before we need to wake up and refresh the display for memory. In summary, the display system improvements were key to achieving the Ryzen 6000 battery life goals. We now show a first on x86 processors: AI-based dynamic noise suppression. In today's workplace of hybrid work and constant communications, we've all experienced background noise distractions on conference calls. The purpose of this capability is to reduce unwanted background noise on audio and video calls and leave the human speech. The new Ryzen 6000 feature uses a neural network running on our audio coprocessor to suppress background noise dramatically. This is enabled on certain OEM systems. The key advantage is power savings versus a more heavyweight CPU processing-based algorithm. Next, we will show more about how this works and why it saves power. Here we show the block diagram of the active noise suppression. Starting with the left side of the block diagram in orange, we show model parameters stored in DRAM. Parameters are streamed into local SRAM on the audio processor using a DMA engine with bursts that are coalesced to save power. The neural network runs within the audio coprocessor. The most important part of the diagram is that the CPU, GPU, and the majority of the rest of chip on the right side of the diagram can be in lowest power state and run the network with much lower power than CPU-based schemes. In summary, this feature gives us a good example of how we are approaching platform-level optimization problems and solving them with efficient SoC design capabilities. Finally, we reach the fifth element of optimization in Ryzen 6000, the software level, specifically the AMD Power Management Framework. The top-level vision is to enhance the user experience with smarter, quieter, more efficient power control mechanisms. PMF is a software framework which allows customers finer-grained control over performance and power management policy settings. Inputs can come from sensor inputs, from temperature and power information, OS, application information, etc. Output capabilities are system configuration parameter updates such as system power limits, fan policies, etc. Ultimately, this framework can enable a notebook experience better tailored to what the user wants, such as a silent profile as shown on the plot, or schemes which move to other regions of the graph based on system inputs as described. With the software PMF level, we reach the final level of notebook optimization, and this brings us to our summary. And so we conclude this technology tour of the Ryzen 6000 series processor. We've shown how the new technologies plus the optimization approach has yielded an SoC which is great for energy-efficient x86 workloads, great for 1080p gaming and graphics workloads, great for connectivity to all the latest platform technology, and finally, with great long-lasting battery life. Our legal department would like you to be aware of our disclaimers. I'd like to thank you for your attention, and a thank you to all my colleagues at AMD for making this product possible.
Thank you, Jim, for the excellent talk. There are quite a few questions, a lot of interest. I'll ask as many as I can. The first one is from Christian Klinger, and he asked, could you please give more details regarding the optimized design libraries?
The optimized design libraries is a little beyond the scope of the presentation, so I won't be covering that in detail here.
All right, fair enough. The next one is from Joshua Gregory from Chips and Cheese. So regarding the Microsoft Pluton security processor, as you mentioned, we are not going to ask you any details on that, but are you able to disclose how this interfaces with the rest of the SoC? For example, is it presented to the OS like a PSP via the PCI bus, or is it using a different method?
I also would like to not go into the details of the Microsoft Pluton processor.
Okay. The next one is from Charlie Demargian from Semi-Accurate. Ryzen 6000 has a remotely updatable security block that is controlled by a third party, which can run arbitrary code. Is that not a risk?
Specific security questions are definitely beyond the scope of my presentation.
Okay. The next question is from Mark Heckman. Do you see a path to offering true Thunderbolt I/O as opposed to the USB 4 so that you can match Intel or at least on a spec sheet?
That would get into unannounced product offerings from AMD, which I am not going to discuss.
Okay. The next one is from George Kozma from Chips and Cheese. Can you write from memory directly to L2 with Ryzen 6000 because of the delayed L3 initialization?
The delayed L3 initialization does not impact the path to memory at all. It's simply a control mechanism for making the PC6 resume more efficient. So no impact there.
Okay, great. Next one is from Amarveer Chana from University of Cambridge. Is the audio coprocessor using licensed third-party IP or in-house IP?
That specific level of detail is beyond the content of my presentation, so I can't go into that.
All right, so I had a question. You mentioned that you have power state changes on a thread basis per thread control in the CPU. What is the granularity? Because the activities can change quite rapidly.
You mean granularity in terms of the
power state changes, switches between high and low and whatever states you have.
Do you mean on a like a per time basis?
Yes, on a part-time basis.
Yeah, I mean that depends on the specific power state. We basically have a hierarchy of power states with deep states that have longer longer latencies up to very fast states such as the light C state that I mentioned that operates on very fast microsecond level latencies.
All right, thank you. Thank you for answering all our questions. And that completes this talk, the very first talk. And let's all thank Jim for the excellent talk. Thank you, Jim. So we are ready to move to the next talk in this session. This is on the Meteor Lake and Arrow Lake, Intel next generation 3D client architecture platform, and the Foveros technology. And the presenter will be Wilfred Gomes. Wilfred, please take it over.
Hello, I'm Wilfred Gomes, Intel Fellow, Microprocessor Design and Technologies. I'm joined by my colleague Slade Morgan, an Intel Senior Principal Engineer. We'll be presenting on behalf of our colleagues at Intel Corporation insights into how a PC client architecture is evolving to deliver next generation experiences by realizing the benefits of several key enabling technologies that have been under development for decades and how they finally come together in our upcoming Meteor Lake and Arrow Lake architectures. From my 25 years of designing client architectures, I know that demands on client PCs are changing. We started with performance-based personal computing, where monolithic workloads ran on monolithic chips, and Dennard scaling drove improvements. Then functional additions like networking, connectivity, and mobility, with increased IP integration enabled by design and architecture, led us to build platforms for the diverse workload that with demands from cloud, edge, and now AI. As we look forward, we see immersive experiences driving computing ever higher and harder and demanding even more from our computing devices. Delivering a broader, richer set of experience to users means we must be experience-driven in our architecture and design. What does that mean to us as architects? We need to consider experiences first, working backwards from the diverse user experience models and the corresponding design targets. We also need to deliver the right attribute to this point, trying to spread performance across a general market segment, hoping something will fit or stick is inefficient. The performance needs to be purposefully curated for the experience. We also need to be dynamic, allowing for freedom for designers and product planners to adapt quickly to changing markets in order to remain timely and relevant. Finally, we must deliver scale, which means we need to be able to scale up to a large number of design points and systems that support all these ecosystems. That really means that client architectures going forward must be foremost performance driven with a singular focus on both absolute performance and performance for what, and the ability to offer diverse and multitude versions of IPs and functions. This needs to be matched to an innovation pace to allow time to market and offering the most suitable process node to be selected for each function as needed. All of this needs to be delivered at scale to drive the next exponential of computing, which I will cover in this talk. I want to spend some time talking about disaggregation. The topic has gained a lot of attention and has created a lot of talk over the last few years. And with no surprise, there are advantages by utilizing multi-chips close to others, or building MCPs, or building blocks like tiles. We can arrive at architectures which have higher flexibility, faster refresh rate, and maintain cost effectiveness. However, there's always a performance tax, latency and complexity, and power consumption introduced by moving data from block to block. In this paradigm, monolithic designs were always better when it came to needing outright performance. The disaggregated designs added overheads and sacrificed performance. Of course, the ideal is to have the best of both the worlds, a monolithic performance with disaggregated architecture benefits. But is that possible when you must contend with the challenges of high volume manufacturing? How could we achieve that goal? Today, I'll touch on some of the foundations of such an architecture and how we have brought together the right forms of technology, architecture, and design which have helped Meteor Lake set a new precedent. Disaggregation has been buzzworthy for the last few years, but Intel's journey has been nearly a decade long. As well as Intel's first foray into tiling, it was first client architecture that utilized CPU and chipset partitioning. Since then, we have been steadily advancing. What we learned over this time is that there are actually different ways of doing disaggregation that yield different results depending on the underlying technologies you leverage. To make this clear, I'd like to break our journey into multiple parts: process, technology, packaging, and architecture choice. From Haswell onwards, we progress along each path, making improvements in turns and demonstrating advancement through all our products. These products have shipped in billions of units and are a common mainstay of today's computing. We achieve this by leveraging the optimal architecture partitioning with organic packaging. Kaby Lake G also utilized partitioning but advanced to 2.5D and added external foundry silicon for graphics. Our first 3D packaging product, which was Lakefield, also introduced hybrid architectures and multiple nodes. We finally went all out with Ponte Vecchio, which had up to 47 tiles, utilizing both 2.5D and 3D with our second generation Foveros and incorporating multiple process nodes from multiple fabs. Ponte Vecchio taught us how to create 3D architectures with very high yield and gave us the confidence to bring this technology to the client roadmap. As this audience knows, not all transistors are the same. There are many types. Process technologies can, at a material and microstructural level, optimize the transistors in a block or within a library for a node, and the entire process nodes can also be optimized. The relationship is not one-to-one, and a diversity of different transistors needed to best target the design to achieve different uses and products. By having the freedom to use different transistors in different blocks and tiles, and the freedom to select different nodes, the architecture can be more precisely targeted. The path from standard packaging, which existed mainly to protect and provide power and signal I/O to the underlying silicon chip, has been very innovative. But over time, we have brought new technologies to improve the pace of packaging innovation. The first one has been EMIB, and EMIB allows us to create highly integrated tiles. An example is our existing Sapphire Rapids product for the data center. Now, starting with Lakefield, we've introduced Foveros, our logic and logic 3D stacking technology, and this has an exciting roadmap continuing with Foveros Omni and Foveros Direct that allows us to scale bump pitch and achieve unprecedented amount of density in terms of both I/O per millimeter and the power for these interfaces. The Intel's Foveros process technology allowed us to move to fully 3D die-on-die stacking, and this is a highly scalable technology from the loosest bump pitch to the tightest monolithic-like bump pitch. At the same time, it offers us the ability to disaggregate compute tiles and base tiles in a very flexible fashion, allowing us to create every architecture that is possible. When we built Foveros, the number one constraint was to create a technology that could scale to high volume manufacturing at scale, and this required us to co-optimize across many aspects of the overall architecture of this process. This involved selection of the right bump pitches, the right base layers, test, and also figuring out how to get to high performance and to high yield. Once we created Foveros, we extended this to create Foveros Omni. The Foveros Omni technology extends our 3D stacking to bring multiple base dies and multiple compute dies and the ability to connect I/O directly to the package using copper pillars for the highest performance parts. Then we bring forward Foveros Direct, which utilizes direct copper-to-copper connections to dramatically reduce latency and increase density. With hybrid bonding, we can scale the pitch to enable disruptive architectures. We can then combine all these technologies to create the right architecture for the right segment. Having this roadmap gave us the confidence to align the client architecture and the roadmap to Foveros. The next path is really architecture. It's really important that we select the right building blocks to build all the products. Architecture is the right balance in trying to figure out the complexity and the ability to scale to high volumes with the new layers of abstractions. We have made jumps in abstraction every decade. Today, our largest designs have recently crossed 100 billion transistors, and in the future, we are looking forward to getting over 1 trillion transistors. And if you look at the graph, we are moving to system scale integration to drive the next exponential in Moore's law scaling. Now, bringing this all back together, as I'm sure already predicted from the title of this talk, the culmination of the journey as a result in our upcoming product, Meteor Lake, bringing to bear all the advantages ideally suited for the experience era. So with that, to discuss the architecture and design trade-offs, I want to hand it off to my colleague, Slade Morgan, who will cover that for us. Yes, Slade?
Thanks, Wilfred. Let's dive a bit deeper into the architecture and the key blocks of Meteor Lake to explain how we're implementing this new flexible tiling. Our goal was to get disaggregation benefits not achievable with monolithic design, all the while keeping disaggregation taxes to a minimum. Here are some of the key elements of the Meteor Lake architecture. We have a disaggregated core tile, we have a disaggregated graphics tile, and by the way, graphics has very different performance characteristics from media and display, so we separated those out. With the critical compute elements disaggregated, we can spin the IPs and get them into the right process at the right time. We use a lot of different core tiles in the Meteor Lake family. Different products want different core counts, different mixes of performance and efficient cores, different cache sizes, and we have the ability to flexibly and easily target each segment without disrupting the rest of the design. Over the life of the product family, new generations of the core become available and new process nodes become available, and we pull them in as soon as they are ready. Graphics is scalable in exactly the same way. We scale both the execution units and the cache sizes, and again, we rev these with the new IP and with the new process nodes. Our goal is to scale graphics performance from very low power mobile configurations that all the way up to discrete card-like performance on the laptop. The SOC tile focuses more on ultra-low power. This tile has IPs like media, imaging, display, AI, and the connection to memory. And these can be targeted differently based on the segment. Not all the segments need the same I/O. We offer an I/O extender tile where segment-specific I/O can be created. The I/O extender offers a scalable method to create new segments and leverage blocks across platforms. Now that I've revealed a little bit of the architectural information for Meteor Lake, Wilfred will talk about the actual construction of the part, specifically focusing on the innovations and the technologies needed to create this product.
Thank you, Slade. Now I'll help you put it all together. Several innovations were needed to create Meteor Lake. We first started out with the high-yielding assembly scheme, which uses a 36 micron pitch to enable the assembly of many tiles. We have enabled a backside metallization with solder TIM to support a large range of segments and TDPs. We can also test each tile independently and put them together at high yield. There are 3D capacitors in the base die, fine pitch routing that enable low latency die-to-die connections, and thick metal layers for power delivery. Now you're looking at the base die here, the key to the Meteor Lake construction. The base die has been created to solve power delivery, die-to-die routing, and also the ability to be modular with active silicon. Meteor Lake uses a passive die to first bring the disaggregation concept forward. The design has been put together and is highly scalable and can have several die-to-die designs and can be tiled close to monolithic. We can create many tiles and the methods to have many wires across this tile. The Foveros die interconnect shown is created using extremely fine pitch routing tracks on the base die, and we have designed this interface to be close to monolithic, and this can be done with low power and latency. We can disaggregate across different interfaces and support various bandwidths. The interface is a forwarded clock and created a completely decoupled tile design, allowing us the flexibility to put together various tiles independently. The most difficult aspect of partitioning is the high bandwidth, low latency interfaces. We can partition the die across coherent and non-coherent links and across memory and I/O protocols. We are able to fit a large number of wires, in this case 2K wires, in a small area, and we can have multiple such connections. The CPU is partitioned across using our IDI protocol. The GPU uses the ICXL protocol, and this ICXL protocol is the CXL protocol without the PHY. The I/O extenders can be connected using just the main fabric or just using the PHY interface. Now, once we put all this together, we really had to solve many issues in thermals, and there were several innovations in floor plans, materials, and the ability to add the right interface materials. This has allowed us to build the highest performance parts, enabling us to open thermal envelopes compared to the previous products. So one of the critical issues that we need to solve in creating a high performance product is power delivery. And there were issues that we had to solve in decoupling, voltage regulators, I/O mix and match, form factor, and package optimization. So for this, we bought our highest density 3D capacitors for the base die, and these 3D capacitors helped us to smooth out noise, perform, and get our IPs to perform using really good load lines, and also to enable voltage regulators to be integrated and to mix IPs from different fab nodes. Now, what I'm going to show here is the result of this long journey with improvements in multiple technologies is shown here, and we have been able to increase the number of tiles, increase the amount of bandwidth, and a lot of these improvements compared to our traditional architecture, which started out with organic packaging. For example, the I/O per millimeter, we got 10x improvement. In terms of power, we have gotten over a 5x improvement, significantly lowered latencies. And the Foveros die interconnect that we have allows us to create a highly tiled architecture with several tiles that can be aggregated together. So now we can answer the question of whether we have created a scalable architecture that approaches monolithic. Now with that, what I'll do is I'll pass it to Slade, who will walk us through some of the performance attributes of this new architecture to show us where we stand.
To connect our tiles, we chose a 36 micron interconnect pitch. At this pitch, the power and latency taxes of disaggregation are very small, and we also get very good attach yield. Whatever small penalty exists is handily overcome by the benefits that disaggregation brings. And as the pitch scales further, the taxes get smaller and smaller. In the graph on the right, you can see what we all know, which is that performance improves with each process generation. And we're not only targeting each IP to the process that suits it best, we're enabling the earliest possible intercepts. Our goal has been to bring forward 5 nodes in 4 years, and our disaggregation strategy allows us to accelerate our node offerings. Just as the processes improve, so does the IP. Using disaggregation, we can bring new core IPC every year without disruption to the stable parts of the design.
Thank you, Slade. We cannot give a talk about Meteor Lake without showing some glamour shots. Indeed, the monolithic nature of this product is evident in the tight tiling of the tiles, the modularity of which, thanks to disaggregation, allows us to produce a wide variety of products that are highly scalable and target specific users. And I'm also thrilled to note that Meteor Lake parts are booted and are working in our labs. So the modularity of our disaggregation approach allows us to cover multiple performance points across a range of TDPs, covering from mobile performance to the desktop, just like our existing platforms. It now starts with Meteor Lake, the first tiled disaggregate architecture with the compute tiles on Intel 4. With the architecture scalability and process optimizations, we can move across generations and enable power and performance. Looking forward, we remain at the forefront with the successor to Meteor Lake, which is Arrow Lake, made using Intel 20A. Arrow Lake uses the same construction and swaps out the tiles for newer process options and new cores and graphics. The follow-on product is called Lunar Lake and has the next generation Foveros implementation with a 25 micron bump pitch. Lunar Lake improves the architecture to scale into lower power envelopes. So our experience-first client approach drives the new era of system-level integration to deliver monolithic performance with disaggregate benefits. A co-optimization across process, packaging, and architecture together make Meteor Lake the first tiled disaggregated architecture in Intel 4, and this architecture is extremely flexible and scalable across design points and into the future. Looking further out, we have created a foundation to scale the architecture to create a large range of power performance points and scale this architecture from mobile, edge to AI and to power the era of the XPU. And this architecture is flexible across process nodes, building blocks, and is stackable, can be multi-layer, enables logic on logic stacking, and to build to power the next billion computers and continue Moore's law well into the future. And finally, if you're interested in winning some cool prizes, match my headshot to this logo that you see on the slide, and you'll be entered to win either a NUC PC or other goodies. And again, on behalf of Slade and all my colleagues at Intel, we thank you for attending our presentation, and we look forward to answering questions in the upcoming Q&A. Thank you.
Thank you, Wilfred and Slade, for this excellent presentation. Before we move on to Q&A, I wanted to apologize that I missed introducing Wilfred with his bio, which is a very impressive one. So I want to take a minute before we start the Q&A to do that. Wilfred Gomes is an Intel Fellow and the Director of Microprocessor Design and Technology Solutions. A 2-decade veteran of Intel, Gomes has devoted his career to successive generations of x86 CPU development and the needed technologies, including the first domino control synthesis tools, Intel's cache and register file compilers, algorithms for the out-of-order memory, and execution and techniques designed for designing the x86 core for a range of segments and the required process technology co-optimizations. He's also the co-inventor of Foveros, Intel's 3D integration technologies, and helped bring to life Lakefield, Ponte Vecchio, Rialto Bridge, Meteor Lake, Arrow Lake. He's responsible for the construction and system optimization of the next generation of Intel CPU products and bringing together the holistic set of technology ingredients to enable zeta-scale computing this decade. Before joining Intel, Gomes served on the technical staff at Cadence, Boston, as a member of the Verilog hardware languages and helped develop the logic RTL synthesis algorithms. All right, so going into the question and answer, Wilfred and Slade, are you guys online for that?
Can you hear me?
Yes. All right. So the first set of questions comes from Youngmin Choi from Seoul National University. I'll read out one at a time. Is the base tile manufactured with Intel 16 or Intel 7 process?
Base tile is on Meteor Lake passive die, and it's a very close SIP of 1222, which was used in Lakefield, which is Intel 16.
Thank you. The iGPU and LLC are separated into different tiles. Can the iGPU still access the LLC as previous generations?
Yes. So when we had this disaggregation, we wanted to first use the right protocol to connect our tiles. So the GPU in the past was tightly connected to the cache and was coherent with the last level cache. We still keep the same coherency, but it's over CXL. So both for current traffic and for IO traffic, it can access the memory system and the hierarchy of the CPU. Yes.
All right. The process nodes for GPU, SoC, and IOE tiles are still not disclosed. Is there any chance that these process nodes for those tiles can be changed?
So first of all, the Meteor Lake, Arrow Lake, and the Lunar Lake architecture is a platform, and one of the things that you saw today was They're highly flexible. You can mix and match process node, GPU, and CPU architecture. Having said that, today we are not disclosing the exact process nodes against each of the architectures, and that will be disclosed in the future.
All right, fair enough. Amarveer Chana from University of Cambridge asks, does Meteor Lake contain any SRAM cache or SoC functionality in the base tile, like in Lakefield or Ponte Vecchio? And if not, why was this choice made?
So first of all, the first problem statement was to get a scalable disaggregation strategy that could be brought to scale to a very large number of segments. And so we adopted both architecture and a methodology by which it's highly scalable. So the least common denominator could be just the disaggregation. But in the future, if you look at it, we've already talked about an XPU roadmap, and we will discuss future options against different product segments and users for the base die much into in the future.
All right, thank you. A couple of questions from Ivan Stenger. Are Meteor Lake tiles intended or planned to be used across the product ranges like iGPU tiles, or they are mostly intended for the Meteor Lake and Arrow Lake families?
So obviously, with the system scale integration, there are a lot of possibilities. Think of the Meteor Lake, Arrow Lake architecture as a platform. So when we build this, a whole lot of reviews are starting. So obviously today they're used in the client family. There are a lot of possibilities in the future. I cannot talk today about what could be the use of such tiles, but I think what really opens up is the different opportunities for reuse across many different segments.
Okay, there's room for only one more question. Rest of it, please answer on the Slack. There are a lot more questions, but will Meteor Lake and Arrow Lake be integrating the Microsoft Pluton processor?
I cannot talk about that today here.
Okay, and I'll ask one final one here from Arn Varhede. Are there monolithic Meteor Lake prototypes, and did Intel make a cost analysis like higher packaging and interposer cost? Doesn't the interposer make the CPU bigger, resulting in much bigger cost?
So just like how we did the Haskell disaggregation, where we separated out the CPU and the chipset, and that has stood the test of time for the last decade. The Meteor Lake, Arrow Lake architecture actually is a ground-up disaggregated architecture where we went through all the different blocks, disaggregated it into the right architectural partitioning across CPU, GPU, SoC. And in the least common denominator, the architecture is built to be, like close to monolithic. It can boot up on its own without extra tiles, and that can hopefully in the future go into other segments. So if you do look at the holistic product cost across, it does use advanced packaging. Advanced packaging does have higher costs, but from a product perspective, the products are lower cost and they scale up and down the thing. As I've said, our exercise on Meteor Lake, Arrow Lake is not to create a point product, but really create a highly scalable architecture that can go from the lowest power to the highest TDP. And again, that would mean both from power and cost.
Okay, thank you. Let's all thank our speakers, Wilfred and Slade. Thank you.
Thank you.
The third talk in this session is Dimensity 9000, a flagship smartphone SoC. And the speaker is Ericbill Wang. Ericbill Wang is currently the Assistant General Manager of Computing and Artificial Intelligence Technology Group inside MediaTek. He has 20 years of experience on IC design and led x86 Northbridge design and verification methodology and ARM-based high-performance and low-power CPU in application processors. His current focus is designing best-in-class CPU PPS. So Ericbill, please take over.
Ladies and gentlemen, my name is Ericbill, and it's my honor to be here sharing MediaTek's latest flagship smartphone SoC, Dimensity 9000, with you. The presentation was co-authored by MediaTek and ARM. MediaTek started the journey to flagship smartphone from Dimensity 1000, announced on 2020 Q1, followed by Dimensity 1200 on 2021 Q1. Dimensity 9000 is a true flagship SoC, delivering a record high Antutu score over 1 million. D9000 is manufactured using the TSMC N4 process and is equipped with latest ARM CPU, Mali GPU IP, an in-house 5th generation APU, and the low-power DDR5X up to 7500 megabits per second. It supports up to 320 megapixel image capture, advanced Wi-Fi and Bluetooth connectivity, and features an integrated Release 16 5G modem. While the modem design is perhaps the most complex feature of the SoC, it is largely driven by standard compliance. It's usually the CPU, GPU, and APU that differentiate the user experience. These are what we will focus on today. So, what makes a great smartphone SoC? From performance requirement, today's display support up to 144 Hz refresh rate. Lots of features like Face Beautify are added to camera applications. The resolution and frames per second of gaming ever increasing. These drive higher CPU, GPU, and APU performance. From a user experience perspective, instant response when launching an app or rendering a web page are must-have. Users also want to play smooth 3D games for an hour or more without overheating the phone. From device form factor perspective, the power budget and battery capacity remain roughly constant due to thin and light requirement. To address the requirement space and boundary condition, high performance and low power processors are critical. Let's look at CPU's challenge closer by checking a typical smartphone power budget curve. Each point on the curve represents how long the device can run before thermal throttle under given total system power consumed. The application launch takes 1 to 2 seconds and has the highest power budget. Benchmark type application typically run 100 seconds or more and have somewhat lower power budget. Both of them are able to use highest CPU frequency, and their power budget bounded by junction temperature. The 1-hour gaming scenario has a much lower power budget, bounded by skin temperature or the external temperature of the headset. We need the CPUs to run medium to high frequency while maintaining a sub 1 watt per core power budget. For extended use application like video playback, the total system power consumption must be maintained below 1 watt and thus not bounded by thermal. The challenge is low power for longest operating hours. Given different CPU performance and power requirement across a wide performance range, MediaTek proposed worldwide first tri-gear CPU architecture on mobile phone back in 2016. Max-gear CPU focus on short burst workload and is optimized for highest peak performance. Mid-gear CPU focus is on sustainable workloads like gaming and is optimized power for gameplay required performance. Min-gear optimization targets lowest power for maximized daily usage hours. Note the concept makes sense. Our first trial did not end up well. There are two learnings I'd like to share with you. First, it's very important to choose CPU type and the implementation recipe to correctly shape the usable power efficiency curve. By drawing a straight line between the highest and the lowest performance point, we can find mid-gear CPU in left figure did not provide better efficiency and merely plug a small gap between max and the min gears. In contrast, the D9000 on the right achieves a more normal power trend over the whole performance range, with the mid gear being a significant contributor. Second, we had to significantly upgrade our scheduling technology from a rule-based to a per-die energy-aware task placement, which directly use energy as a cost function. At the same time, we changed the operating frequency decision from periodic to event-based whenever task was assigned or removed from the CPU. Combine above two improvements, we are able to pick up right CPU and run at just enough frequency per the loading. Next, let's dive into CPU 6. D9000 contains one ARM Cortex-X2 running up to 3.05 GHz, 3 ARM Cortex-A710, and the 4 ARM Cortex-A510, where the 8 CPUs connect to the ARM DynaIQ Share Unit, or DSU, containing cache coherency logic and the 8 MB shared level 3 cache. Compared to D1200, our previously highest performance SoC, we see 40% IPC improvement on max-gear CPU, 35% IPC improvement on min-gear CPU, and 50% power reduction at parity performance, thanks in large part to the latest ARM CPU IP and the TSMC N4 process. The IP level improvement translates well into CPU benchmark score, more than 30% improvement on Geekbench versus D1200. Next, let's look at key microarchitecture improvements on CPUs and the DSU. For max-gear CPU, ARM Cortex-X2, the integer performance increased 16% over Cortex-X1. The front-end design, the branch prediction is decoupled from fetch, This allows faster run ahead and the ability to hide the taken branch bubbles from the code. Conditional branch prediction accuracy was improved by larger prediction state and then an alternate path predictor. We see significantly improved on branch miss prediction per kilo instruction across various workloads. In the out-of-order core design, a pipeline stage at this page was removed, resulting in an overall 10-cycle pipeline. The out-of-order window increased 30% to harvest more instruction-level parallelism. For back-end design, low store structures increased 33% to track more in-flight requests. Data prefetching algorithm was improved from both coverage and accuracy perspective. As a result, the backend stall was substantially reduced. For mean-gear CPU, Cortex-510 integer performance increased 35% versus Cortex-A55. Considering typical workloads running on the mean-gear CPU are not so heavy, a merged core microarchitecture was designed to increase area efficiency without degrading real use case performance. With this microarchitecture, two cores are grouped into a complex. The level 2 cache, level 2 TOB, and the vector data path are dynamically shared within a complex. Next, we will move to cluster level. The DSU is responsible for cross-CPU cache coherency and supports shared level 3 cache for all CPUs. There is a trend of increasing level 3 cache size in smartphone SoC, previously 1 or 2 MB to 8 MB today. The higher performance CPU and larger level 3 cache support added challenges to DSU design. In DSU 110 microarchitecture design, the level 3 cache, snoop filter, and control logic were separated into slices based on address. This allows multiple requests to access different slices in parallel, hence increasing bandwidth. A ring-based transport network connects the cores to the slices and bus interface. Specifically, a bidirectional dual ring structure was utilized to shorten paths between components and optimize latency. While the structure greatly improves snoop and level 3 access bandwidth, the power overhead is a concern, especially for light loading scenarios like video playback. An innovative power mode was created to partially shut down level 3 RAMs and associated logic. An integrated hardware power controller makes it easy to transit between different power states and deliver state-of-the-art power management. Overall, the microarchitecture enabled 2x bandwidth improvement and 25% leakage reduction versus previous generation. The leakage can be further down to 75% lower with partial shutdown. The DSU IP also supports level 3 cache partition. allowing us to allocate different number of ways to different CPUs, which is very useful for QoS feature. Today's system contains a lot of background tasks for housekeeping, which can degrade foreground application performance by occupying level 3 cache and evicting critical task data. CPU QoS technology was developed to address this challenge. By leveraging the Android framework, we could split critical and non-critical tasks. The criticality tag is attached to CPU by the scheduler during task placement and becomes a sideband signal to guide level 3 cache allocation. An adaptive algorithm was developed to runtime optimize allocated way number for non-critical tasks. We see 14% speed up for application launch stress test and minus 5% power on 120 frames per second QQ speed gaming. Next, let's look at GPU 6. D9000 GPU contains 10 ARM Mali G710 cores running up to 955 MHz with a 2 MB shared level 2 cache. Compared with D1200, the D9000 GPU delivers 2.2x peak performance and 1.5x power efficiency. It enabling a new standard for popular mobile games like PUBG at 90 frames per second. Contrasting GPU and CPU, there are a few fundamental differences. GPU workload can be highly parallel versus CPU, which allow us leverage multi-core strategy for power efficiency. GPU demands higher DRAM bandwidth than CPU, which obviously consumes higher DRAM power. GPU require CPU to translate high-level API like OpenGLES into GPU commands, which consumes substantial CPU power. 3 key knobs adopted on D9000 to address above challenges. First, we push the minimum operating voltage from 0.6 volt to 0.5 volt. Combined with a GPU core count designed for GPU bound gaming, we can run with a 10% reduced voltage. Second, by enlarging the GPU level 2 cache to 2 MB and system level cache to 6 MB, we can reduce 15% bandwidth. A new compression engine enhances the emerging popular HDR format, which further saves 10% bandwidth. Third, we reduce 15% GPU driver overhead by offloading GPU execution scheduling task from CPU to an embedded processor inside the GPU. Looking now at the GPU microarchitecture, D9000 integrate ARM Mali G710. Compared to ARM Mali G77 used in D1200, Mali G710 equipped 2x Texel and FMS capability under same frequency. As execution engine consume more than 50% of power in shader code, the execution engine was redesigned for power efficiency. 4 processing elements were put inside the execution engine and shared one special function unit. Overall, Mali G710 performance density is 1.2x versus Mali G77. Comparing real gaming experience on Genshin Impact from D1200 to D9000, the frame rate increased from 42 to 60 frames per second when playing 10 minutes. It increased from 33 to 50 frames per second when playing 30 minutes. Moving on to the APU. There are many kinds of AI applications desired by smartphone users, such as face unlock by visual perception, camera bokeh effect by object construction, noise reduction and super resolution, which help to improve the image quality, and the speech application that make your phone a smart personal digital assistant. D9000 is equipped with a 5th generation APU designed by MediaTek. It contains 4 performance cores and 2 flexible cores. Compared with D1200, it delivers 4.3x performance and 2.8x power efficiency. With such improvement, we enable flagship AI features on camera capture and sustainable video. Let's look at the detail. As we know, thermal and memory bandwidth are rare resources in smartphone, and this is more challenging to AI due to its high computation and memory access nature. Our APU microarchitecture was designed with this challenge in mind. We support versatile data type and operators from 4-bit integer to bfloat 16 format. An efficient MAC architecture maximizes data reuse, and some additional bandwidth reduction text to be covered on the next page. There are 2 major bandwidth reduction techniques adopted. First, deep layer fusion allows almost all temporal workloads data to be exchanged through internal memory. 65% bandwidth reduction on 4K 30 video AI noise reduction by this technique. Second, we define tile-based direct control and data link interface between ISP, APU, and display. The tile data can stream to and from APU without touching DRAM. 24% bandwidth reduction on Full HD 60 AI super resolution application with this technique. For AI applications, optimal data type is application specific. For example, 4-bit, 8-bit integer is sufficient for classification, while 16-bit floating point is needed for speech recognition. Consequently, a single data type is not optimal considering hardware performance and power efficiency. Consider a network trained with 32-bit floating point. Moving to 8-bit integer is great for performance and power, but the porting effort is high and accuracy may drop. On the other hand, the power consumption by staying at 16 or 32-bit floating point is currently not affordable in a smartphone. Our APU supports a mixed precision data type in a single network model to take advantage of both data types. We see a 6x improvement in inference per second with a 75% reduction in energy per inference by mapping to 16-bit floating point network with 80% of the layers quantized to 8-bit integer. As I mentioned earlier, high performance and low power processors differentiate the flagship smartphone user experience. Our optimization involved processor IP subsystem and SoC hardware software design. We are glad to share with you the work and be part of the global force pushing the technology envelope forward. Finally, I would like to acknowledge our team's effort and ARM's partnership to make Dimensity 9000 happen. Thank you.
Thank you, Ericbill. Let's all thank our speaker. Hi, Ericbill, are you online?
Yes.
Okay.
Could you hear me?
Yes,
Yeah.
I can. We have only a few minutes for the Q&A, so I'll try to get through as many of them as I can. So the system level cache that you talked about is smaller than the CPU L3 cache. Could you tell us the motivation and the guiding factors for sizing these caches?
Yeah. So when we plan we try to make the CPU required cache into level 3. And the system level cache was mainly for data exchange outside the CPU, which is the GPU and ISP. So the sizing of the system level cache mainly driven by the GPU and multimedia usage.
Okay. Another question from Christian Klinger. Do SRAM memories in the GPU also run in 0.5 volts?
So we are using dual rail SRAM. So the peripheral rail is able to run below to 0.5 volt, while the bit cell is maintained at CVCC, 0.75.
All right. So a question from Helene Wang. What do you think about supporting FP8 format on the APU?
Pardon?
What do you think about supporting FP8 format in the APU? You talked about FP16, so can you go down even more in the FP format size?
Okay. I think I probably could answer this offline.
Okay, that's great. So another question from Andreas Farber. Does Cortex-X2 contain any software visible instruction set features that differ from A710 or A510?
Yeah, I can take that. So the answer is that the Cortex-X2 supports the same instruction set as the other two CPUs. I know the question asks about not seeing product pages regarding Cortex-X1 and X2, and that's because these are part of the custom CPU program, and these are not part of the standard roadmap. But from an ISA perspective, Cortex-X2 supports the same ISA as A710 and A510.
Okay. One last question here, and you can keep answering on the Slack, is a couple of questions. What is the operation frequency on the DSU? Does the DSU also support the frequency scaling? And does the SoC maintain the cache coherency between the CPU cluster and the hardware accelerators such as the GPU and the APU? First,
Okay.
what about the frequency?
Pardon? Could you? So DSU able to run up to 1.6 gigahertz, 1.6, and able to support the DVFS by itself. It can change the frequency and voltage by itself. Also, we support the I/O coherency between GPU and CPU.
All right. Thank you. And let's all thank our speaker again.
Thank you.
Okay. So we move on to the last presentation in this session. And it is on the next generation Intel processor built for the edge, Intel Xeon D 2700 and 1700. And the speaker is Praveen Mosur. Praveen Mosur is an Intel Fellow and Chief Technologist for Network and Edge Platform Architecture in Network and AMP Edge Group, NEX. He is responsible for delivering efficient Xeon Scalable and Xeon D platforms with optimized software and AMP accelerators for network applications that are deployed in 5G, Edge, Enterprise, and Cloud. Praveen is recognized as an expert in network workloads. He has delivered significant innovations that span platform, CPU microarchitecture, ISA, hardware acceleration in the CPU and IPU, and associated software. Praveen has also published 12 technical papers, holds 19 patents, and has 13 pending patents. He holds a bachelor degree in electrical engineering from Osmania University, Hyderabad in India, and a master's degree in electrical engineering from Auburn University. So with that, over to Praveen for the presentation.
Hello everyone and welcome. My name is Praveen Mosur. I'm excited today to share with you additional details on how we architected and built the new Xeon D processors. So let's get started. The new Xeon D processors that we will talk about today come in two product categories. The Xeon D 2700 processor family, which scales up to 20 cores, and the Xeon D 1700 processor family, which scales up to 10 cores. These processors were built for the edge and architected for the edge native applications. And when I say it was built for the edge, it's because these products were architected and developed from the grounds up, targeting network, 5G, IoT, and other edge usages and workloads. The processors have integrated accelerators, integrated Ethernet, and a flexible packet processor for efficient network performance. And all of this has been optimized for dense form factors and deployments in ruggedized environments. I'm going to first start off by sharing some of the guiding principles we followed to architect the next generation Xeon D processors. Our goal for these products were to provide a continuum of efficient computing from cloud to edge on the same architecture. This scalability will enable developers to deploy their applications in a consistent manner from cloud to edge. To achieve these objectives, we need to deliver server-class performance with the best latency and power across a broad set of workloads and usages prevalent at the edge. After some internal evaluations, we chose the Intel Xeon architecture as our starting point. And we optimized the architecture for the power and compute scalability that is required for the edge deployments. So in summary, the critical factors for an efficient edge processor are compute performance supplemented with workload accelerators and integrated Ethernet so we can enable developers to meet the tight SLAs and latency. Second, we need to include security capabilities to enable developers to protect data in flight, in rest, and when the data is being processed. And finally, all of this needs to be available in optimized packages to enable dense form factors. Now let's dive in and take a closer look at the product capabilities and how we met these objectives. To enable the dense form factors, we decided to support the product in two optimized BGA packages. The Xeon D 2700 processor comes in a 52.5 mm by 45 package. while the 1700 comes in a 45 by 45 package. The heart of the SoC is the compute, and we are using the next generation core for these products. The new compute core delivers massive improvements in crypto and AI performance. It also supports Intel Secure Guard extensions, or SGX, to enable trusted computing at the edge. These cores will access the memory controller through a monolithic mesh, which includes the shared last level cache. This SoC architecture allows for more consistent latencies, which are a critical requirement for real-time edge applications. Also, there are no NUMA domains for developers to be concerned about in this architecture. Now let's talk about the interfaces of the SoC. For memory bandwidth, we support 4 channels on the 2700 processor, while the 1700 supports 3. We're introducing PCI Express Gen 4 in the Xeon D product line, and the 2700 processor supports 32 PCI Express Gen 4 lanes, while 1700 supports 16 lanes of PCI Express Gen 4. Now, in addition to the PCI Express Gen 4 lanes, there's a separate bank of 24 high-speed I/O lanes that can be configured to operate as PCI Express Gen 3, SATA, or USB 3. In addition to these essential I/Os, the next generation Xeon D processor also integrates 100 gig enterprise-grade Intel Ethernet controller and the next generation Intel Quick Assist technology. I want to highlight a key capability that we're introducing in the 2700 processor, on the left of the picture, inline IPsec. This capability enables Ethernet packets to flow more efficiently between the Ethernet controller and the crypto blocks. Inline IPsec is highlighted in the green connection between the Ethernet and the QAT blocks on the 2700 block diagram on the left, and we'll talk more about this during our presentation. But let's get started with a deep dive by looking at the compute. We chose the Sunny Cove core for the next generation Xeon D processors because of its excellent power and performance metrics. This core was developed based on our learnings and deep insights from both cloud and edge workloads. We made significant improvements in Sunny Cove to enable great out-of-the-box performance for a wide range of workloads. The table on the right compares the Sunny Cove microarchitecture details with its predecessor, the Intel Xeon D 2100 processor. As you can see from the table, we have a massive increase in the out-of-order window that allows for more micro-ops to be executing in the pipeline. To feed the micro-ops, we increase the number of loads and stores. We also increase the L1 data cache by 50%. And finally, the last level cache has also been increased, but the latency to the last level cache remains at 14 cycles. In addition to these microarchitecture changes, we also have new workload acceleration instructions in Sunny Cove. Think of workload acceleration instructions as performance multipliers for that workload. For example, let's review the crypto workload acceleration instructions. Sunny Cove core introduces several new crypto instructions, some of which utilize the AVX512 data path and execution engines. Specifically, vector AES-NI and big number arithmetic or integer fuse multiply add instructions. These new instructions result in exceptional crypto performance gains. Now let's review the table on the right. The top table is showing the bulk crypto performance measured using OpenSSL speed on AES 256 GCM. The second column in the table is the Xeon D 2100 processor, which is our baseline 1.0. The third column shows the performance gain based just on the microarchitecture improvements in the new Sunny Cove core, and that's an impressive 1.53x over the baseline. But the last column is the performance multiplier I referenced earlier, vector AES-NI. This is our first example of a workload acceleration instruction, and it enables 3.4x increase in performance for AES 256 GCM. One more example in the table below. The columns are similar, but the rows are now for asymmetric crypto algorithms or public key cryptography. As an example, in the first row of the second table, the popular RSA-2K sign operation, using OpenSSL speed and the new AVX512 integer fuse multiply add instructions, we are measuring an impressive 4.3x increase in performance. These new capabilities in the core enable software optimizations and innovations. We're partnering with ISVs and open source communities like OpenSSL and DPDK to make these innovations available transparently so developers see benefits to their applications in a more seamless manner. Let's review one additional example of a new workload acceleration instruction that Sunny Cove enables. AI at the edge is a critical workload, and there are many usages and requirements for enabling efficient inferencing and machine learning at the edge. Based on Intel AVX512, the Intel DL-Boost Vector Neural Network Instructions, or VNNI for short, delivers a significant boost in performance by combining 3 instructions into one. This maximizes the use of compute resources, utilizes the cache better, avoiding potential bandwidth bottlenecks. The table on the right shows the performance gains due to VNNI when compared to the baseline AVX512 instructions on the 2700 family of processors. On ResNet 50, the popular image classification model, VNNI provides an impressive 1.8x increase in performance. Now let's talk about trusted execution. The security of data and code, while it is at rest or being processed, is critical to the overall trust and the integrity of applications. This is especially true when the deployment is at the edge. Sunny Cove Core and the next generation Xeon D processor supports Intel Software Guard Extensions, or SGX. SGX allows Ring 3 applications to launch an enclave. Once the enclave is launched, the code and data in the enclave are cryptographically protected from the underlying infrastructure. And the underlying infrastructure can include hypervisors, OS, drivers, or even BIOS. Because the trusted execution is at a Ring 3 enclave, only the necessary code and data is included in the enclave. This has a huge benefit of further reducing the attack surface for adversaries. So in summary, Intel SGX enables trusted computing at the edge and adds another layer of defense by reducing the attack surface of the system. Now let's move on from the compute to the accelerators. In Xeon D 2700 processor, we have integrated the next generation Intel Quick Assist technology. This technology provides hardware acceleration for bulk crypto, asymmetric crypto. Now let's move on from the compute to the accelerators. In Xeon D 2700 processor, we have also integrated the next generation Intel Quick Assist technology. This technology provides hardware acceleration for bulk crypto, asymmetric crypto, and lossless data compression. Compared to the previous generation, it has support for new crypto algorithms that are being used in the industry, specifically Cha-Cha-Poly, SM3, and SM4. The SM algorithms are PRC specification, and now we have them accelerated in hardware. In this generation, Quick Assist also introduces a new capability, inline acceleration. Look-aside accelerators are accessed from software running on the cores using an API call. In the block diagram on the right, these requests will flow through the host interface that you see on the top. The request is then processed, and the response is sent back to software. As part of the Gen 3 Quick Assist technology, we've added a new interface that we call Inline Packet Interface. This new packet interface will allow IPsec packets to flow directly from the Ethernet block to get access to the bulk crypto services. The pictures here in this slide further illustrate the look-aside and inline acceleration models. The model on the left is look-aside acceleration. We need this path because more often than not, software running on the cores have to manipulate the network packets or buffers before accessing hardware acceleration. A good example for this, for instance, is TCP reassembly in the TLS protocol. On the right is the new inline model. This offers better latency, lower memory and fabric utilization, and higher performance. However, inline requires the data path and the logic to understand the packet flow and the protocols to implement that in hardware. In this generation, we have chosen to implement IPsec, a popular and a stable protocol using this acceleration model. The reason we added support for inline IPsec was driven by usage models and the need for unlocking additional acceleration as part of our Intel Ethernet controller. But before we discuss the inline architecture further, let's review the performance gain using Intel Quick Assist technology in look-aside mode. Transport Layer Security, or TLS, is a widely used client-server protocol. The protocol enables trusted connections by using public key encryption standards. The graph on the right shows the relative performance of Nginx TLS secure web server when running on a Xeon D 2700 processor. The performance data is collected on 4 cores, 8 threads. Compared to the baseline implementation, which is the blue bar, the optimized software provides 2.5x increase in performance. This optimized software uses the Sunny Cove workload accelerator instructions that we discussed earlier. Finally, the last bar is the Quick Assist technology performance, and that is an impressive 4x increase in performance compared to the baseline software implementation. Now let's switch gears and talk about the integrated Ethernet capabilities. The next generation Xeon D processors integrate enterprise-class 100 gigabits Ethernet controller. This controller supports advanced offload features that will accelerate packet processing. For instance, it supports application device queues, or ADQ, that aligns device queues with specific applications to minimize interrupts and latency. This enables higher performance on latency-sensitive applications. The controller has a fully programmable pipeline to enable frame classification for advanced and proprietary protocols. It also supports advanced scheduling and RDNA over IWARP or RoCE v2 protocols. Now let's come back to the inline IPsec model that I referenced earlier. As shown in the picture on the bottom right, Xeon D 2700 processor also integrates a flexible packet processor and switch in addition to the Ethernet controller. And here's how we architected our inline IPsec flow. Packets entering the switch from the bottom right of the picture of the page will be classified by the flexible packet processor. When it detects an IPsec packet, it sends it to the Quick Assist block for crypto processing. Once the packet is decrypted, it is routed through the switch to the Ethernet controller as clear text packet. This now enables offloads that are supported in the Ethernet controller to be used because now the packet is in clear text. I'd like to use this packet pipeline to further articulate the benefits of inline IPsec because it goes beyond the performance attributes that we'll discuss shortly. The top half of this pipeline shows the receive path. The Ethernet link is on the left and it connects to the cores on the right. When encrypted packets enter this pipeline, unless we decrypt the packet, the rest of the accelerators in the Ethernet controller, which is towards the right of the pipeline, cannot perform the parsing and classification of the packets because the packets are encrypted. So we architected inline IPsec to decrypt the packet within the Ethernet pipeline. This now enables the clear text packets to be parsed and classified in the Ethernet controller. So inline IPsec not only offers efficient crypto offload, but also enables post-crypto classification. Now let's look at some performance data on IPsec. IPsec is a network security protocol. It is used extensively to protect peer-to-peer network connections. We support this protocol in 2700 Xeon D processors using multiple mechanisms. First is software, and we reviewed the impressive performance gains from workload acceleration instruction, vector AES-NI, a few slides ago. The second is using hardware acceleration, look-aside hardware acceleration, through the Intel Quick Assist technology. And the third, for the first time in the 2700 Xeon D processors, is the inline IPsec capability. The chart on the right shows the relative performance based on these three solutions. X-axis is the frame size or packet size in bytes, and we have two data points, 512 bytes and 1420 bytes. Y-axis is the IPsec relative throughput measured on the clear text side. As the chart illustrates, inline IPsec provides superior performance because it has the highest percentage of the IPsec pipeline offloaded in hardware. Now, depending upon specific performance requirements of a usage model, developers can now choose the right acceleration model for their application. I want to now come back to the guiding principles for this product. As I mentioned earlier, the goal of this product was to enable seamless experience when applications moved from cloud to edge. We wanted to provide a continuum of compute from cloud to edge on the same architecture. We chose the Intel Xeon architecture because it is widely deployed in the cloud, and we believed it can scale to the low power targets that we had for this product. And we can see the power or TDP scalability that we achieved using this architecture in the chart on the right. The two bars on the right of the chart are the third generation of Intel scalable Xeon processors. And the new Xeon D processors that we've been talking about extends that architecture all the way down to 25 watts while integrating enterprise-grade Ethernet and acceleration. We achieved this impressive scaling by building this product from the ground up, optimizing the SoC architecture and implementation for edge workloads. For example, we optimized the compute core, the SoC fabric. We also retargeted the voltage frequency operating point of this product for edge deployments, and packaged all of this innovation in two BGA packages for dense and ruggedized deployments. I would like to share with you a couple of examples of the exciting form factors that the next generation of Xeon D processors are enabling. The system on the left is fan-cooled and designed for indoor use. But a chassis was also developed for outdoor environments, making the platform dust-proof and waterproof. Now, this enclosure can be used to mount it to a ceiling or a lamppost. The white plastic cover called radome, this is a material specifically designed so that RF signals can pass through. And on the right of this picture is the daughter card, a COM HPC module based on the Xeon D 1700 series of processors. This form factor is 6.3 inches square, very compact. One last technical bit of information. You might be familiar with Power over Ethernet or PoE. A customer asked us if we can build a system where we can have this entire server run over PoE for an edge deployment. And this architecture delivered. This Xeon D server can be run over 2 links of PoE++. We discussed a lot of things, and I hope you found it interesting. But I want to leave you with 3 key messages about the new Xeon D processors. It was built for the edge, from the ground up, for the software-defined network and edge workloads. We scaled the Xeon architecture for edge deployments which have constraint and power requirements. And finally, the new Xeon D processor comes with built-in AI and security workload instructions, integrated crypto, compression acceleration, and enterprise-grade Ethernet controller. Thank you very much for your time. And finally, if you're interested in winning some cool prizes, match my headshot to this logo that you see on the slide, and you'll be entered to win either a NUC PC or other goodies.
Thank you, Praveen, for this stimulating talk. Let's all thank our speaker first. All right. For the Q&A, Praveen, are you online?
Yes, I am.
All right. So let's go. We have a bunch of questions. Let's see how many we can get through here. The rest you can keep answering on Slack. Nathan Brookwood asks a couple of questions. You mentioned PCI Gen 4. Why not a PCI Gen 5? Does that mean that no CXL as well?
That is correct. No PCIe Gen 5 or CXL. And the rationale was we were integrating a lot of the IOs, specifically Ethernet and accelerators as part of the die. We just didn't see a need for PCI Express Gen 5 for this class of product.
Okay. He also asks, does the 1700 include the flexible packet processor?
That is a good question. 1700 does not include the flexible packet processor. And the rationale that we took is to provide a low-cost, more optimized TDP and package. And that was the trade-off that we had to do, was take out a few of the functionalities that the 2700 has. So the 1700 does not have the flexible packet processor.
All right. Christoph Novak asks, why did you decide not to include Q83 on the D1700? Is it also a cost play?
It is exactly right. It is. It's a function of cost play and trying to make sure that the power or TDP gets down to the low level of 25 watts. 1700 scales down all the way to 25 watts, and the only way we could actually get to that point was to reduce the capabilities relative to the 2700 processor.
All right. The next one is, why are there so many SKU options in the Intel product specifications?
That's a great question. Usually customers actually ask for more, and a lot of the optimization to be able to get to certain very specific targets, it requires us to do some engineering work to ensure that the product meets that particular SKU target. So once that engineering effort is done, we tend to put it out for other customers so they have a better choice. And I would also note that this product, unlike the predecessor, is going into both network, storage, and some data center applications as well. And that requires, the slew of SKUs. Yes.
All right. Fair enough. Karthik Swaminathan from IBM Research asks, does Xeon D support AMX, the advanced matrix extensions?
No, not yet. So that would be in a future processor. It does not support it.
All right. Sayantan Sur from NVIDIA asks, what is the TDP for the Xeon D2700?
We'll have to look at that SKU stack, but if my memory serves right, it starts at 65 watts, and the chart that we reviewed was, I think, up to 140 or 120 watts rather.
Okay. So if you have more information, you can answer on the Slack.
Absolutely. So please ask me that question on Slack, and I can give you the pointer.
One more here. Youngmin Choi from Seoul National University asks, it seems the datasheets of some of the recent Xeon processors, ICX, CPX, etc., have not been publicly released. Any reasons?
I'll actually find the link, and it should be available. There should not be a problem there.
So to round it off, I had a question that, you mentioned a whole bunch of things that you guys did to make it an age-appropriate processor. So out of those, what do you think are the biggest things that you did that made it suitable for an age compute?
That's a very good question, Devjit. I think when we started out this program, the form factor and everything else drove the BGA, so that's not a major ask. The biggest ask, I would say, is integration of new technologies, right? The enterprise-grade Ethernet, the flexible packet processor. That was probably the biggest decision we had to make, it required a lot of engineering effort. And other things was related to figuring out how we take a server class CPU and scale it all the way down to 25 watts, which actually meant we had to work very closely with our customers to see what they can trade off, what features they want to trade off at a 25 watt SKU as opposed to say 100 watt SKU. That choice was very required a close interaction with the customers to be able to say, yep, you can remove that, and so on and so forth.
All right. Thank you so much. That completes the Q&A. Thanks our speaker again.
Thank you, Devjit, and thank you
So
all.
this concludes the final session of the conference. Thanks for staying for so long. And with this, I'm going to hand over to Gabriel Southern, our vice chair, for concluding remarks. He does so much heavy lifting, and I'm sure he will be happy to, give some remarks.
So thank you everyone for participating and attending Hot Chips 34. I'm Gabriel Southern, the vice chair for Hot Chips this year, and I'm just going to give a few closing remarks. So first, just really quickly, talk about what happens next. There's a few questions about that. Basically, the conference is over, but you can still look at the replay if you want. The slides will be available. Slack will remain up for about 90 days. Basically, they're changing their policies now. Before, they just kept 10,000 messages. Starting in, I think, September 1st, they just keep the last 90 days. So on the slide here, it notes that you can still register and watch the replay. We're, I think, going to have a reduced price if you register late, so there'll be information about that posted online soon. Of course, if you're watching this live, you've already registered, but you'll be able to tell your colleagues if if they're interested. And then everything will be publicly available sometime later this year, probably in December. So now just a few slides to thank everyone who's made Hot Chips 34 possible. First, thanks to all our sponsors. I'm going to go through this pretty quickly, so I'm not going to read them all, but it's really great that we have the sponsors supporting us, and it helps keep the costs down for attendees and really makes this conference accessible to lots of people. Thanks to the organizers. Everyone who puts this together is a volunteer. No one's getting paid, but we all do it because we're interested in it. We enjoy the engineering, and we enjoy presenting this technical information. So glad for everyone who participates on the organizing committee, the program committee, steering committee. We also have a lot of volunteers who help us set up our studio, answer questions on Slack, do registration, everything that's sort of not the organizing committee stuff, but we need a bunch of people during the conference itself. So these people, again, not getting paid, just doing it because they like helping out, and so really appreciate their help as well. The presenters, obviously, we wouldn't have a conference if people didn't present, and it's a ton of work to put together these slides and put together the presentations and present the hard work that people have done. So again, thanks to everyone who's done that. And thanks to all the poster authors. You can find the names on the actual website more easily, but this just kind of gives a sense of the scale of Hot Chips, of how many different people are involved in putting this information out here for you and putting together a good conference. And of course, thanks to all the attendees. As of when I put these slides together, we had 1,700 registered attendees. We've had many questions on Slack, lively discussion. I've seen stuff on Twitter, articles in the press. So really, there'd be no point in having Hot Chips if we didn't have people participating. So really glad to see all of that. So now I'm going to talk a little bit about what's sort of the future of Hot Chips. And to start, let's look back at the past. So this was information I went and looked up on the website. It's showing from Hot Chips 1. I'm not going to read it here, but you might be interested to look at the slides. But basically, kind of, what was the purpose of Hot Chips? Why did people organize it? Back in 1989, the first Hot Chips held at Stanford. And it's basically saying, hey, we wanted to get together and present the latest in, microarchitecture, microelectronic technology. We didn't want to have a bunch of marketing stuff, and we wanted to be able to, let professionals who attended the conference learn. And I think that mission has really served Hot Chips well, and it's lasted for 34 years thus far, and I think we're doing well, and lots of people who attend hopefully think we're doing well. So it was I think the right mission, and we're trying to keep it going. So if we talk about Hot Chips present, obviously we're not at Stanford right now. So this some pictures of the setup we have here, the studio, sort of where I'm standing right now, and people off to my right who have a bunch of computers and sound systems and all this stuff to try to put together a professional looking conference. And patch in people from Zoom. So it's a lot of work, and it's going to be a lot of work to take all of it down. So I won't explain everything right now, but just wanted to give an idea of what we're doing today and what went into putting this conference together and being able to share it with you. And then thinking forward to the future, obviously prior to the pandemic, we'd held Hot Chips in person for decades, and then the past 3 years, it's been a virtual conference. And the virtual conference is not the same as an in-person conference. There's some benefits and there's some downsides. So one of the questions we had when you registered is say, if you are interested in Hot Chips in 2023, how do you think you want to participate? And about 70% of people said, hey, I'd rather just be online. 30% say, well, I really want to have the in-person conference, even though it's going to cost more. So that's the sort of some statistics that we have. And it was also interesting that kind of the split between people who are, hey, I want it online, but I'm local, I live in the Bay Area, versus I want it online, or I want it in person, but I'm traveling from wherever, from England. And one guy emailed me and said, hey, it'd be a lot more convenient for me to have Hot Chips in person so I could just fly here from England. It's, I don't want to watch it online, in a different time zone. So what we need, sort of final ask of you, the attendees, is please fill out our survey so we can get a little bit more detail than just, that's a couple questions we had on the registration. Survey is pretty short. If you just want to fly through it and don't give any detail, there's just 6 required multiple choice questions. You can do it in less than a couple minutes. Or if you want to give us more information, there's also some forms to fill in additional thoughts you might have, additional comments. And if you give us your email address, what you use to register for Hot Chips, you'll be entered in a raffle to possibly win a $100 Amazon gift card. So that's not really the reason to do the survey, but it's kind of a small carrot to go ahead and fill that out, chance to win. So with that, thanks, and hope to see you next year.